net positive suction head. So that is the net pressure head which is required to be maintained at the suction side of the pump. So suction side of the pump is where we usually get the minimum pressure because we need that fluid to be sucked into the pump. So that's why that is the location where we have got the minimum pressure. So then we discussed that there are two net positive suction heads. One is net positive suction head required. So this is the suction head which is determined by conducting experiments, and usually it is provided by the manufacturer. While the positive suction head available, which is the second suction head, so that depends upon the altitude of the pump installed and then other factors. So if we remember that in the last class we discussed about that how we can calculate net positive suction head available. So for that we considered this geometry as it is shown in the figure. So here the storage tank is below the pump. So it means that we have to kind of suck that water into the pump. So it means that here at the entrance of pump, which is location 2, the pressure should be lower than this pressure which is here, so that it can be sucked into the pump. So it means that if we apply the energy equation between the three liquid surface, which is point 1, and a point on the suction side, which is point 2. So a suction side is basically the inlet of pump, and the pressure side is the outlet of pump, right? So then if we apply the kind of energy equation, then we can just write that P1 is equal to P atmospheric, which is point here, and then V1 is equal to 0. Why is that? Because we are taking it a large container, then Z1 plus it is because on the negative side, so it is minus Z1. So you can see here that it is with a minus sign here. Because if our reference is this point, this this the installation point of that pump, then because the storage tank is on the north side, so that's why we have got minus Z1 because it is in the minus Y direction. Now here on the right hand side we have got on the suction side the pressure is PS, so PS upon gamma plus, and then the velocity at the suction side, that is Vs square over 2g and plus Hn. So Hn is the losses inside the this point 1 and 2. So it is due to the friction loss, which is the major loss occurred, which is going to be occurred in this pipe length, and then minor loss, which is due to this kind of 90-degree turn, and then the flow coming into the pipe from the reservoir. So all those losses will be coming into minor losses, right? And we discussed those minor and major losses in chapter number 8. Now, as you remember that if we want to find the net positive suction head, then we need to have the stagnation pressure at the suction side, which is PS upon gamma plus Vs cube upon 2g, and minus PV upon gamma. PV is the vapor pressure of water at that temperature. So if we rearrange that PS upon gamma plus Vs square upon 2g, that is the stagnation pressure or available head at that pump impeller inlet, and then because we need to subtract minus PV upon gamma, so if we subtract it on the left hand side, it would become equal to net positive suction head available. And then here on the right hand side, because we are subtracting it on the left hand side, so we need to also subtract it on the right hand side. So that's what we did here. So the left hand side, which is this two terms minus PV upon gamma, that is net positive suction head available. And on the right hand side, there is an additional subtraction of minus PV upon gamma, as I explained earlier. So now we can measure net positive suction head available at different volume flow rate, and then we can compare it with the net positive suction head available required at that volume flow rate. So it means that in order to have pump operation without cavitation, we need to make sure that net positive suction head available is always greater than net positive suction head required. So here, for instance, in this diagram, this net positive suction head available decreases, while the net positive suction head required increases with the volume flow rate. And if we increase the volume flow rate to a sufficient large value, then we can see that there is a point after which the net positive suction head required would become greater than net positive suction head available. So it means that if we operate the pump in this way, after this range of the point of intersection between these two suction heads, then there would be a occurrence of cavitation, which would kind of damage the blades of impeller, and so that it is not very desirable. So it means that the safe operating volume flow rates are on the left hand side of this vertical red line. So we need to make sure that whenever we kind of select a pump for a given volume flow rate, so we can compare the net positive suction head available with the net positive suction head required, so that there is no cavitation occurring. So let's do a numerical problem of
So
this. Yeah. Yes.
जो कैविटेशन वाला ये ग्राफ के अंदर सर वो स्कीम कलर के अंदर तो सारे पॉइंट जहाँ पे ज्वाइन कर रहे हैं दोनों से पहले भी कैविटेशन होगी इसके
Acha, Umair Khalid, if you see here that for the cavitation to occur, let me explain it on the whiteboard. So give me one. That was let me draw this graph here. Okay, so we have got it is volume flow rate here, and then here we have got two curves. One is net positive suction head required, which is provided by the pump manufacturer, right? So they conduct experiments at each volume flow rate and then lower the pressure at the section side of the pump to determine that at which point there is a cavitation occurring. And then there is another head which is called, okay, let me draw it with a blue line. So this is net positive suction head available, right? So net positive for the safe operation of pump without cavitation, net positive suction head available should always be greater than net positive suction head required. So it means that this is the intersection point. So on the if we operate the pump on the right hand side of like the volume flow rate higher than this value, so here there is a possibility of cavitation. But if we operate it on this side, no cavitation. The medical problem that how we can calculate net positive suction head available, because as I have told you that net positive suction head required, that is being provided by the manufacturer, right? So if we look at let me show it here, that here you can see a line required net positive suction head. So you can see that required net positive suction head, that for that the range of that head is given here 0, 2, 4, 6, 8, 10. So if you see these lines, they are somewhere here 20, 40, 60. So it means that if we kind of draw this line here, so it would come somewhere here like this, because it is starting from maybe 2, so it should have been drawn somewhere here, but in order to clearly show it on a different scale, they have drawn it like this. So I hope that and this data is provided by the pump manufacturer. So let us do one numerical problem now to see that how we can calculate these things. So after that we can do we can move on to the next topic. So, uh, okay, so now we have got here. Okay, without reading the statement, we can see a pump which is installed at point 2, and there is a reservoir which is at point 1. So, first thing we note here that the reservoir is at a higher altitude. So, it means that in net positive section head there was a minus at one term. So, for this case, it would be plus Z1, right? So now you can see that now the possibility of cavitation would be a little bit less because the altitude is not minus, it is not being subtracted from the equation, but it would be added here plus Z1 because here why it was minus because the storage was below the pump location, but in this numerical problem the storage is above the pump location. So it means that that one would be added here. So that one minus that two basically. So if we now we read the statement here, the 11.25-inch impeller option of the TACO model 4013 FI series centrifugal pump is used to pump water at 25 degrees centigrade, at which point rho is 997, new value is also given, and vapor pressure, which is the saturation pressure, at which you can find from the thermodynamic table as well, right? That if you go into the thermodynamics steam table and you see the value of the saturation pressure at 25 degrees centigrade, you would find its value equal to 3.169. So if we have got 100 degree, then it is like 100 kilopascal. So we know that. So from a reservoir whose surface is 4 feet above the center line of the pump, so it means that Z2 value is equal to 4 feet. So, no, it means from a reservoir whose surface is 4 feet above the center line, which means that Z1 minus Z2, that is 4 feet. I I hope that you can understand this, that they are saying that the difference in altitude between the reservoir surface and the center line of the pump inlet, which is this Z1 minus Z2, that is basically 4 feet, right? So now the piping system from the reservoir to the pump consists of 10.5 feet of cast iron pipe with an internal diameter of 4 inch and an average inner surface height of which is epsilon, which is 0.02 inch. There are several minor losses, which includes a sharp edge inlet, KL value is 0.5, then 3 flange smooth, 90-degree regular elbows. We can see those elbows somewhere here, 1, 2, 3, and there are flanges here. You can see the flange here in the diagram, right? So then KL value 0.3 each, then and a fully open flange blow valve. So there is a flange blow valve which is also installed to control the volume flow rate which is coming into the pump. So that even if it is fully open, it would have some kind of flow disturbance. So that the KL value is equal to 6. Then for this pump uh, pump system, we need to calculate the available net suction for net positive suction head, and it should be NPSH at a volume flow rate of 400 gallon per minute, which is equal to 0.0253 meter cube per second. And then afterwards, we need to determine the maximum volume flow rate that can be pumped without cavitation. So it means that they need to calculate this Vmax in this location. This is the Vmax. So this is the maximum volume flow rate at which there would be no cavitation. Above this value, there would be a possibility of cavitation, and below this volume flow rate value, there wouldn't be any cavitation. So first of all, first thing first, we would calculate the available net suction positive head at a volume flow rate of which is given 400 gallon per minute. Right. So let's start with the energy equation here. So it is better that if I can copy this figure somehow here. So let me do that. Okay. So this is our figure. So if we write the energy equation between point 1 and point 2, we can write that P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2 plus HS. Right. So now in this equation, if we kind of want to do simplification, so we know that V1, if it is a large reservoir surface having a very large area, then it can be equal to approximately equal to 0. Then we so and then P1 is equal to P atmospheric because it is kind of exposed to atmosphere. So if we write it and what is P2 here? P2 is PS, which is the pressure at the section side of the pump, right? So if we and what is V2? V2 is Vs, which is the velocity at the section side of the pump. So if we put in the values here, then we and now I am trying to write P2 upon rho g plus V2 square upon 2g on the left hand side because it would give us the net positive section head available. So it would be PS upon rho g, which is this one, plus Bs square upon 2g. And now if I write this one here, it would be P1 upon rho g plus Z1, right? Okay, now we need to also get these two terms plus Z2 and plus HL on the left hand side, which is effectively the right hand side here. So Z1 minus Z2, because when it would go here, so it would become Z1 minus Z2 and it would become minus HL. Right. So I hope that this point is clear. Now, in order, as we know that net positive section head available, that is equal to PS upon rho g plus Vs square upon 2g minus PV upon rho g. Right. So PV is the vapor pressure at the given temperature of the fluid. So in order to introduce net positive section head available, we need to subtract minus PV upon rho g on the left hand side as well as on the right hand side. So if we do that, then PS upon rho g plus V s square upon 2g minus PV upon rho g is equal to P1, which is P atmospheric in this case upon rho g plus Z1 minus Z2 minus HL minus PV upon rho g. Right. So now what is this Z1 minus Z2? That is the height difference between reservoir free surface and the center line of the pump, which is 4 feet in this case, which was given to us. Yes. 1 minus Z2, that is 4 feet as given. So let me write here. It would be this whole term. This would be equal to nbsh available, and then here we have got again P atmospheric divided by rho g plus Z1 minus Z2 minus HL minus PV upon rho g. Right. So now what is the HL summation here? That is we know from chapter number 8 knowledge that HL is equal to F L upon D V S scale upon 2G. Right. Okay. And the second thing is that this is the major loss and the minor loss is KL upon VS scale upon 2. Right. So this is the atom. So let me write. This is the major loss due to friction, and these are the minor loss due to components and inlet outlets. Inlet outlet. Right. So now, do we know VS? We don't know that because Vs is the velocity. So in order to get the value of Vs, we need to calculate it from the volume flow rate at which we need to do the calculation. That is 0.0253 meters cube per second. So here, if I want to calculate the velocity inside the pipe, which would be equal to Vs, that would be equal to volume flow rate divided by the cross-sectional area, which would be pi by 4 d square. So volume flow rate, that is equal to 0.0253 divided by pi by 4 into what is the d square here, that is 4 inches. So first of all, we need to change it into the meter square. So 4 into 0.0254. So we know that in 1 inch there is 25.4 mm. So and in 1 inch there would be 0.0254 meter. Right. So if we do the calculation, the velocity comes out to be equal to 3.112 meter per second, which is the velocity inside the pipe. And then we know now we need to calculate the value of f, which is the basically the which can be calculated by the calculation of Reynolds number. So Reynolds number calculation we can do it. So Reynolds number is equal to rho Vs into diameter divided by mu. Rho and mu values are given in the data. If I can show you, where here it is rho value 997, mu value is also given, and then Vs we have calculated. Diameter we know that 4 into 0.0254. So if we put in the value, then its value comes out to be 3.538 into 10 to the power 5. And we also know epsilon value, which was given in the data, which was equal to 0.02 inch. So epsilon upon E would be equal to 0.02 inch divided by 4. So that would be epsilon upon T value would be equal to 0.02 divided by 4, and then it would be equal to 0.005. And then again, by using Reynolds number and epsilon upon D, if we go into the Moody chart or use the Colebrook relation, we can find the value of F, as we learned in chapter number 8 as well. So if we find the value of F, that becomes equal to 0.0306. Right. So as we have calculated here, so this is good. Only thing which is left is the summation of Kl, which is the loss coefficient in the component. So if we go through the statement again, there are losses given. So Kl 0.5 sharp edge inlet. So summation of Kl would be consisting of 0.5, which is due to the inlet. Then we have got three we have got three flanged smooth 90-degree regular elbows. Like one elbow is this 90 degree, then again 90-degree elbow, and then again 90-degree elbow. So they are three elbows. So for each one, KL value is 0.3. So and for the three would be 3 into 0.3. And then there is a glow valve. So its value is equal to 6. Flange no more. So these values can also be determined from the table, but in exam it would be given to you or the table. So in either way, you need to determine KL value for each component. So if we determine that, it becomes equal to 7.4. So after that, once we have calculated the KL value, we need to just put it in the this equation, which is HL, and so and then we can calculate HL, and once we calculate HL, and then we can kind of calculate the nbsh, because we know the P atmospheric, that is 101.325 kPa, and then that one minus that two is 4 feet. We can convert it into meter very easily, minus HL we have just calculated from here, and then uh, in this equation, and then PV value it is also given in the equation, PV in the data, which is 3.169 kVA. So if we put in the values, all these values, I hope that you are following me. So P atmospheric 101 kVA, Z1 minus Z2 4 feet as it is given in the data. HL, for HL calculation, F is known to us, which is we have determined it. Then we put in length, total length, it should be given somewhere here. Total length of the piping system is 10.5 feet in the data, and then L upon D, and then all other data is known. So HL can be calculated. PV, that is the saturation pressure at the 25 degree centigrade, which is the fluid temperature. So from here we can kind of calculate the value of NPSH. So NPSH available after putting all these values, that becomes equal to the 7.148 meters, which is equal to 23.5 feet. Okay, any question? The available NPS net positive suction head, it should be NPSS at volume flow rate of 400 gallon per minute, and now we need to determine the maximum volume flow rate in units of gallon per minute that can be pumped. So it means that now we need to first of all we need to know the NPSS required curve, because if I take back here, that if we want to calculate, at this point, which is let me this point, so we need to have this curve, which is NPSH required curve, which would be provided by the pump manufacturer, and then NPSH at we need to determine NPSH at different volume flow rates, so that we can kind of construct this curve, right? Like this. So maybe 4, 5, 6 points. So you can write a small program for that, or you can use either the Excel file, so that once we have got this curve from the manufacturer, which is the black curve, NPSH required and NPSH available, we need to calculate it at different volume flow rate. Like for instance, we have calculated at 400 gallon per minute. So we can change that value to 600, 800, 200, 1000, and then we can kind of construct this blue curve. And then once we get this blue curve, then we can find the intersection point between this black line and blue line, which is the maximum volume flow rate without cavitation. So that is something which it is shown here. This curve here, this net positive section has required. That is the curve on the bottom side of this graph, and then available NPSH at 20 degrees centigrade, which is this curve, which is this one, the top, the curve on the top of the graph, right? So you can see that in that case, NPSH, the maximum volume flow rate becomes 600 if we have got the water available at 25 degrees centigrade. But interestingly, as I also discussed in the last class, that if we increase the temperature of the fluid to 60 degrees, then what will happen in this equation? This PV value, because we know that the vapor pressure increases with the saturation temperature. So if we increase it, then PV upon gamma would increase it, and when PV would increase, which is the vapor pressure, net positive suction head available would decrease, because this quantity is being subtracted. So instead, if the water was available at 60 degrees, then the maximum volume flow rate which we can have in this pump, that would decrease from the 600 to maybe 550. So it means that for the cavitation phenomena, that becomes more when we have got the fluid temperature at higher value, right? So that is something. So these are the physical concepts which you need to build. But in order to build these concepts, you need the information which is required in this equation, right? So now the last part of this numerical, discuss how the maximum flow rate without cavitation can be increased. So how can we increase the maximum volume flow rate? It means that the intersection point of these two curves, net positive section head required and net positive section head available, can be moved on the right hand side. So then again, we need to see at the equation what we can control here. One thing is free atmospheric, we cannot control it very much because usually all the things pumps operate it in at the ground level. So it means that we are that first quantity on the right hand side, that is kind of a constant value. Now, can we change the altitude? Yes, we can. Of course, if we can make that one more and more. This means that if the pump is attached on the higher altitude, then this minus that one could become plus that one, because this minus came due to the fact that pump was installed at the higher altitude as compared to the storage tank. But if the pump is installed at a lower altitude as compared to storage tank, which is the case here. In this case, pump is installed at a lower altitude, then this quantity would be a positive value, which was 4 feet in the numerical. So if we increase this height of the reservoir, then cavitation would volume flow rate would increase, maximum volume flow rate without cavitation. What else? If we can decrease the HL. Now, how can we decrease the HL? Either we use very highly finished pipe in which there is no surface substance, or we decrease this total length between the reservoir and the pump. And what else, that if we can have minimum component involved in the piping system, then this HL would be lower. And then if we can use the fluid at a lower temperature, working temperature, then even then we can increase the maximum volume flow rate without cavitation. So all these parameters, they significantly affect the design of pump, which needs to be operated in a safe range of volume flow rate, in which there is no possibility of cavitation. So I hope that this numerical example would clarify a great deal about the concept that how we can avoid cavitation uh, in a pump. So I hope that these things are clear to you. Now, if there is no query, we can start discussing the next concept. So that is not very difficult. So I would just quickly go through that. That in some applications, because here we are talking about one pump, right? So it is good enough to meet the requirement for a common household. So like in your home, we have usually installed one pump for transporting the fluid from the underground tank to the overhead tank, right? But what if we are talking about the supply of water to a whole sector from a lake, right? Like uh, from the supply which comes from CDA, for example, in Islamabad or in Rawalpindi. So it means that we cannot use only one pump because we need very high high net head, and as well as very high volume flow rate, because it has to go in different streets, it has to go in different sectors. So it means that at the lake from where the water is being taken, we could have kind of a number of pumps installed, right? Not a single pump, because it is very difficult to get only one pump to meet the requirement of whole sector. So it means that there are two options of those pumps to be installed. Either we can install pumps in series, or we can install pumps multiple pump installation. So when we talk about multiple pumps, then either we can install in series, right? So when we install it in series, then we install it to increase the net head available across the piping system, right? And as you know from the electric circuit, that when we have more resistances in series, then there is a voltage potential difference drop across the resistances, but the current remains the same. So what is current in this case? That is the volume flow rate. So volume flow rate would remain the same when we have got the multiple pumps which are installed in series. Now, the second way of installation is the in parallel. So in why we need that panel installation? Because we want to increase the here let me write constant, and here we have got increase, right, when we use this. But for the panel we want to increase the volume flow rate through the piping system, and in this case uh, let me write here. This is point 1, this is point 2. Similarly, this is point 1, and for the point 2, the net head remains constant for the parallel arrangement, right? So constant increase. We know this from the electric circuit as well. If we install electric resistance in parallel, the voltage drop would be the same, and then the current would be depending upon the resistance, individual resistance. So the resistance which has got the lower value, that would have the maximum current, and vice versa. So I hope that you can appreciate the analogies between the flow situations and electric circuits here. So now we can, after this introduction, we can see the implications of installation of pumps, because as I mentioned that when we have got when we need to increase the volume flow rate or the net head, then if we have got pump already installed, like if it is producing like 20 gallon per minute, right? So we need to have 25 gallon per minute. So it means that we need to install a smaller pump in parallel so that we can have a little bit more volume flow rate. But there are some drawbacks or limitation of having a different pump capacity pump. So arranging dissimilar pumps in series or in parallel may lead to problems, especially if one pump is much larger than the other, as shown in these figures. So here you can see what is the consequence here. So if you kind of install this here, then it would kind of the volume flow rate here that would be dictated by this impeller eye of this smaller pump. So that is kind of creating a bottleneck, right? Because now we have installed a very small pump, so even the net pressure head would be increased a little bit, right? But the volume flow rate would be quite restricted due to installation of this small pump. And here because we have got a smaller pump, and there is a chance that there would be a backflow in this smaller pump, because that is kind of a bigger resistance. So there is a possibility of a backflow in this pump. So this is because the pressure rise and volume flow rate are related for a pump. Ranging dissimilar pumps in series may create problems because the volume flow rate through each pump must be same, right? But the overall pressure rise is equal to the pressure rise of one pump plus that of the other. So if the pump have widely different performance curves, the smaller pump may be forced to operate beyond its free delivery rate, whereupon it acts like a head loss. It means that it is not going to so let's suppose that if we say that we need to enforce this at 20 gallon per minute, but because this pump cannot have that capacity, so it means that it is operating beyond the free delivery point. So the free delivery point, let me show you again here. That is the point. This is the free delivery point, which is the maximum volume flow rate possible for that pump. So it means that if it would operate after this point, then it wouldn't be giving any net pressure head to the system. So it means that it is acting like an additional resistance to the piping system. So it has got no use in practical sense. Right, so I hope that this point is clear. Ranging dissimilar pumps in parallel may also create problems because the overall pressure rise must be the same, but the net volume flow rate is the sum of that through each branch. If the pumps are not sized properly, the smaller pump may not be able to handle the large pressure difference in volume rate and the flow in it branch could be reverse flow, as I mentioned that it can have a back flow. This could inadvertently reduce the overall pressure rise. In either case, the power supply to the solar pump would be wasted. So, and what is the other way around of this? What is the alternative? That if we want to increase the volume flow rate or the net pressure head requirement by like 10%, then we don't need to install an extra pump. Then what we can do that we can use a larger pump having a larger impeller diameter, right? So we don't need to kind of go toward the smaller pump, which is very much different in performance specification as compared to the larger pump. So that is the best way. So if the power increase requirement is small, then it is better to increase the original pump speed or input power, replace the impeller with a larger one or replace the entire pump with a larger one. However, there are many applications where two or more similar, usually identical pumps are operated. As I mentioned, that if we want to pump water from lake into a sector like CTA does, so in those cases there are kind of hundred of pumps installed in series and parallel at the location of lake. So and in between that water supply. So because that is not enough only to install the pumps only at the lake location. So when operated in series, the combined net head is simply the sum of the net head of the individual pumps. So that is the same thing as we have done in electric circuits as well. That the potential drop, net potential drop across all the resistances which are installed in series, that is the sum of the individual resistance. And then, okay, so I think these things I would explain in the next slide, next class, I think.